Three interstellar travelers, each on distinct courses, yet their journeys interweave as if threads in an unperceived tapestry. ʻOumuamua, Boris, and now 3 Atlas. Each hailed from the cosmos, followed a trajectory too deliberate to ignore, and departed without pause. They navigated like reconnaissance drones, analyzing atmospheric composition, documenting chemical makeup, and relaying data to an unseen origin. 3 samples, 3 assessments, each skimming past Mars, Venus, and Jupiter, yet deliberately bypassing Earth. It's as though our world's data is already logged, its chemistry recorded, the examination concluded. And 3 Atlas has not merely followed this pattern, it has elevated it to perfection. Stay with us until the end, for tonight we will connect these paths. What we will unveil is a stark reality few are prepared to face. If these enigmas captivate you as they do me, please ensure you click like and subscribe to Cosmo Chill to receive every update as this unfolds in real time. Share your location in the comments, along with the current time there and your thoughts on this new development. And if you wish to support our community's growth, please share this video on X, Facebook, Reddit, or even within your private group chats. Your support is the reason we can continue to pursue stories like this. Therefore, thank you for your backing. Part 1. The precise architecture of 3 Atlas. There are moments in history when the universe presents us with something for which we are ill-equipped. July 1, 2025, marked one such occasion. A network of telescopes in Chile, part of the Asteroid Terrestrial Impact Last Alert System, detected an object traversing the darkness, an anomaly. They designated it 3 Atlas, the 3rd extraterrestrial body ever identified, the 3rd visitor from beyond our immediate cosmic vicinity. And as astronomers charted its course both backward and forward through time, they uncovered something that should send shivers down your spine. Its trajectory is not erratic. It is meticulously planned. Most celestial bodies that venture into our solar system adhere to predictable orbits, ellipses sculpted by the eons of gravitational influence. They circle, they return, they behave. But 3 Atlas deviates from this norm. It orbits no celestial body. Its path is hyperbolic, signifying its origin from an entirely separate region of space and its return to the interstellar void. This much was anticipated. What was not expected was its chosen route through our system. Visualize this scenario. An object enters our solar system at an approximate speed of 60 kilometers per second, which equates to about 37 meters every single second. It approaches from the direction of Sagittarius, from the vast expanse between stars where light traverses immense distances. As it nears, it begins to navigate our planetary system with surgical exactitude. On October 3, 2025, it passes Mars at a distance of 0.19 astronomical units. This proximity is considerable, alarmingly close for an object traveling at such velocity. Then, on October 29th or 30th, pending final calculations, it reaches its perihelion, its closest point to our Sun, at approximately 1.36 to 1.4 astronomical units. This positions it directly between Earth and Mars. Yet, its journey continues. On November 3, 2025, it traverses Venus at roughly 65 astronomical units, and subsequently, months later, on March 16, 2026, it sweeps past Jupiter at 0.35 astronomical units. Mars, Venus, Jupiter, 3 celestial bodies, 3 distinctly chosen worlds. And here's the unsettling aspect. Earth is conspicuously absent from this itinerary. Consider what these 3 planets represent. Mars, the arid planet, the desiccated world, a place where water once flowed and life may have emerged before its atmosphere dissipated into space. Venus, the toxic planet, the scorched world where an unchecked greenhouse effect transformed a potentially habitable sphere into a pressurized inferno shrouded in sulfuric acid clouds. And Jupiter, with its retinue of moons, Europa, Ganymede, and Callisto, signifies the ocean worlds encased in ice, realms where liquid water lies hidden beneath frozen crusts, and where life might still persist in the darkness. It is a sequence, a progression from arid to toxic, to frigidly aqueous, from past habitability to failed habitability, to potential habitability. It is as if an unseen hand has delineated the evolutionary stages of planetary environments and declared, examine these, measure these, catalog these, and Earth is to be entirely overlooked. Now, you might rationalize this as mere coincidence. Space is immense, and objects traverse it without volition or design. Random trajectories are precisely that, random. Occasionally, they align in ways that appear significant to our pattern-seeking minds. However, there is more to consider. The orbit of 3 Atlas is retrograde, meaning it travels in the opposite direction to most objects within our solar system. While its inclination is merely about 5 degrees from the ecliptic, the plane where most planets orbit, its direction is approximately 175 degrees, moving almost perfectly counter to the prevailing flow, yet nearly aligned with the planetary plane itself. This maximizes its potential to intersect with planetary orbits. The majority of interstellar objects arrive at arbitrary angles, plunging through the solar system at wild inclinations, missing all significant points of interest, and then receding back into the void. But not this one. This object entered on a flat trajectory, aligned, and positioned itself amidst the worlds. Furthermore, consider its chemical composition. When astronomers directed the James Webb Space Telescope toward 3 Atlas and analyzed the light filtering through its coma, the gaseous and dusty envelope surrounding it, they discovered something peculiar. The coma is predominantly composed of carbon dioxide, not water, nor the mixture of volatile substances typically observed in comets. Carbon dioxide with a ratio to water of approximately 8:1. This is among the highest ratios ever recorded in a comet. It is inverted, it is anomalous, or rather, it is sufficiently unusual to warrant a thorough investigation. Carbon dioxide is abundant on both Mars and Venus. Mars's tenuous atmosphere consists of 95% CO2. Venus's oppressive atmosphere is composed of 96.5% CO2. And now, an interstellar visitor arrives, rich in the very element that defines these 2 planets, passing both of them in succession. If its purpose were related to Earth, one would anticipate the presence of water or organic compounds mirroring our oceans and atmosphere. But it is not here for Earth. It is here for something else. And this is the aspect that should trouble you. Scientists continue to classify it as a comet, treating it as a natural phenomenon, a mass of ice and rock that originated around another star billions of years ago and was expelled into interstellar space through gravitational interactions. This is the conservative explanation, the logical conclusion. However, when one adopts a broader perspective and examines the geometry, when one observes its precise navigation through the regions of potential habitability, when one notes its enrichment in the exact volatile substance that 2 of these worlds exhale, a question arises. What if this is not random? What if this path was deliberately chosen? Part 2, Trajectory, an in-depth examination from detection to planetary milestones. The initial detection was almost unremarkable. Atlas, the same system that monitors for asteroids posing a threat to Earth, registered a moving point of light on July 1, 2025. Initially, it appeared to be just another piece of cosmic detritus. However, as astronomers reviewed archival images and older observations, they realized this object had been present in the sky for weeks. It had eluded detection. We had all missed it. And once its trajectory was plotted forward and backward through time, the implications began to surface. A hyperbolic orbit. This is the technical designation for an object not gravitationally bound to the Sun. It originated from beyond our solar system and is now departing. The mathematical calculations are unequivocal. When the orbital energy is computed and yields a positive value, it confirms that the object will never return. Mua exhibited this characteristic. Boris did as well. And now, 3 Atlas joins that distinguished group of confirmed interstellar visitors. Its inbound velocity was estimated at approximately 60 kilometers per second relative to the Sun. This is rapid, but not impossibly so. It is consistent with an object that has drifted through the galaxy for millions or billions of years, accumulating speed from the Milky Way's rotation and the gravitational nudges of passing stars. The direction from which it originated, somewhere in Sagittarius, does not correspond to any known star system. However, stars are in constant motion. By the time 3 Atlas departed its home system, assuming it ever had one, that star could be located anywhere. What distinguishes this object is not merely its interstellar nature, but its inclination, a mere 5 degrees off the ecliptic. This is an exceptionally small deviation. Most interstellar objects are expected to arrive at random angles, as interstellar space lacks a defined orientation. One would anticipate an even distribution of inclinations across all possibilities. Yet, 3 Atlas is nearly coplanar with the planets, and its retrograde direction, 175 degrees, signifies its passage through the solar system within the plane where most activity occurs. Imagine attempting to throw a dart at a spinning disk from across a room and hitting its edge precisely. This is the scenario a random interstellar object would face to remain within the planetary plane. Yet, 3 Atlas succeeded. Not only did it maintain its position within the plane, but it also timed its arrival to pass 3 significant worlds sequentially. Let us trace these encounters. Mars first. On or about October 3, 2025, 3 Atlas passes within 0.19 astronomical units of Mars. This is approximately 28 million kilometers. In astronomical terms, this is an intimate proximity. Mars possesses a thin atmosphere with a surface pressure of only 6 millibars, but it is replete with unanswered questions. Methane appears and vanishes. Subsurface ice awaits beneath the regolith. Rovers explore ancient riverbeds, and a constellation of spacecraft observes from orbit. Mars Reconnaissance Orbiter, MAVEN, the European ExoMars Trace Gas Orbiter. As 3 Atlas passes, all these instruments will have a prime vantage point. Next is perihelion, the closest approach to the Sun, situated between 1.36 and 1.4 astronomical units. This places it between Earth's orbit and Mars's orbit. However, Earth itself will not be in its vicinity. We will be at a different point in our annual circuit around the Sun, observing this visitor's turn from a distance. Following that is Venus. Around November 3, 2025, 3 Atlas passes within 65 astronomical units. This is roughly 97 million kilometers. Venus is a world of extremes. Its surface temperatures are high enough to melt lead. The atmospheric pressure is 90 times that of Earth. Its clouds are composed of sulfuric acid. Nevertheless, there is speculation regarding the potential for life within those clouds. Microbes that might subsist in the cooler upper atmosphere, where conditions closely resemble those on Earth. Japan's Akatsuki orbiter is currently observing, and upcoming missions like Da Vinci and Envision will delve deeper. Through this corridor of instrumentation, 3 Atlas will glide. Finally, Jupiter, on March 16, 2026, at 0.35 astronomical units, approximately 52 million kilometers. Jupiter, the king of planets, a gas giant with a magnetosphere so vast it would encompass the Sun if visible. And orbiting within this magnetic field are its icy moons. Europa, with its subsurface ocean, warmed by tidal forces, potentially harboring life beneath kilometers of ice. Ganymede, possessing its own magnetic field and concealed seas. Callisto, ancient and heavily cratered. NASA's Juno orbiter is currently in orbit, ES's JUICE mission is en route, and Europa Clipper will arrive shortly. The Jovian system is under intense scrutiny, and 3 Atlas will traverse directly through it. 3 worlds, 3 distinct stages of habitability, 3 opportunities for an object to sample, to measure, to record. And Earth, the sole planet in this system where life is confirmed, abundant, and evident, is entirely omitted from this sequence. One might argue that Earth is excessively active, too conspicuous, too readily apparent. Perhaps whoever or whatever dispatched this object, assuming it was sent, already possesses knowledge of Earth. Perhaps Earth was catalogued long ago and requires no further observation, or perhaps we are simply not sufficiently interesting. The statistical probability of such a trajectory occurring is low. Some researchers have calculated these probabilities, and the figures suggest less than 0.5% for a random interstellar object to pass this many significant worlds so closely. 0.5%. This is not an impossibility, but it is disquieting. It is the kind of statistic that prompts contemplation as to whether one is observing coincidence or deliberate design. And this is where the instrumentation aspect becomes intriguing. All 3 of these worlds, Mars, Venus, and Jupiter, are under observation. They are monitored. They have spacecraft in orbit or on their way. When 3 Atlas passes, it is not merely traversing empty space. It is moving through regions where humanity has established observational capabilities. Cameras, spectrometers, radar, magnetometers. Every instrument we have developed to study our neighboring worlds will have an opportunity to study this visitor as well. But the question remains, who is observing whom? Part 3, chemical signature, carbon dioxide dominance, and its implications. Comets are temporal artifacts. They are frozen emissaries from the early solar system, or in this instance, from an entirely different star system. Their chemical composition provides insights into the conditions of their formation, including temperature, available materials, and the ambient radiation environment. By analyzing a comet's composition, one is effectively deciphering a narrative written billions of years ago, and the narrative conveyed by Atlas is peculiar. The James Webb Space Telescope, utilizing its near-infrared spectrograph, focused on 3 Atlas and captured the light passing through its coma, the envelope of sublimating gas and dust surrounding its nucleus. The data obtained was unexpected. Carbon dioxide dominated the spectral analysis. The ratio of CO2 to H2O was approximately 8:1, meaning 8 parts carbon dioxide to 1 part water. This represents one of the highest ratios ever detected in a comet. Most comets we study are relatively rich in water. Water ice is abundant in the outer solar system and in the protoplanetary disks surrounding young stars. One would logically expect an interstellar comet to conform to similar principles, but 3 Atlas deviates from this expectation. It is, in a sense, dry. Water is present, but it is a secondary component. Carbon dioxide is the primary constituent. Other volatile substances were also identified, including carbon monoxide and carbonyl sulfide, the expected elements. However, the overwhelming presence of carbon dioxide is the most significant finding. This raises several questions. One potential explanation relates to its formation environment. It is possible that 3 Atlas coalesced in the outer reaches of its parent protoplanetary disk, far from the star, where temperatures were sufficiently low for CO2 ice to condense efficiently. Different regions of a disk exhibit distinct chemical characteristics. The frost line, the distance at which water ice can form, represents one boundary. However, other boundaries exist for different compounds. A celestial body that formed beyond the CO2 frost line might naturally possess an elevated concentration of carbon dioxide. Another hypothesis involves radiation. Galactic cosmic rays, high-energy particles prevalent throughout interstellar space, can induce chemical transformations over extended periods. When these rays impact carbon monoxide ice, they can convert it into carbon dioxide. If 3 Atlas spent billions of years traversing the galaxy, exposed to constant bombardment, its surface chemistry could have undergone significant alteration. Recent studies have explored this possibility. The observed enrichment may not reflect its original composition, but rather the cumulative effect of eons of irradiation. Both of these explanations are plausible and align with natural processes. However, a third possibility exists, one that most scientists are hesitant to entertain, at least in peer-reviewed publications. What if the chemical composition is deliberate? Consider this scenario. If one were tasked with designing a probe to study planetary atmospheres, particularly those rich in CO2, one might imbue it with a carbon dioxide signature. This would allow it to blend in, to appear unremarkable. A comet abundant in CO2 passing Mars and Venus, both planets possessing CO2-dominated atmospheres, would not arouse suspicion. It would simply be perceived as another icy body exhibiting typical behavior, sublimating and outgassing. Alternatively, the CO2 might serve a functional purpose. Perhaps it acts as fuel. Perhaps it is a tool for atmospheric sampling or modification. Perhaps it is a deliberate marker, a signal indicating, "I am here to study worlds with carbon dioxide. Observe me, analyze me, and in doing so, reveal yourselves." This is, of course, speculative. The prevailing scientific view is that 3 Atlas is a natural comet with an unusual, though not impossible, composition. Comets exhibit diversity. We have conducted close-up studies of only a handful of them, most of which originated within our own solar system. It is premature to definitively describe what an interstellar comet should resemble. Each one we discover adds to our knowledge base. Mua was arid, lacking a detectable coma, possibly tumbling and elongated in shape. Boris was icy and active, more akin to the comets we are familiar with. And now, 3 Atlas is CO2-rich, representing yet another novelty. 3 visitors, 3 distinct chemistries, 3 unique signatures. If you were developing a planetary survey network, you would deploy different types of probes to examine varied environments. You would not utilize the same instrument for every task. You would customize, vary the payload, and match the chemical composition to the mission's objectives. However, we are not yet prepared to make such assertions. To do so would entail acknowledging implications for which we are not ready. It would mean questioning whether the galaxy is undergoing systematic examination. It would entail wondering if we are part of an external entity's dataset. It would mean confronting the possibility that Earth is not the primary focus of any attention, but merely one planet among many being quietly catalogued by an unknown intelligence. The chemical signature of 3 Atlas may hold the key. If we can ascertain its isotopic ratios, measure trace elements, or observe behavior not attributable to sublimating ice, we may find our answer. Until then, we are left with a comet rich in carbon dioxide, passing two worlds dominated by CO2 and traversing the planetary plane with geometric precision. And that chemical signature, that distinct characteristic, resides within the infrared spectrum, precisely where our instruments are most sensitive. It is easily detectable, easily studied, almost as if it intends to be observed. Part 4. The Strategic Planetary Corridor. Why Mars, Venus, and Jupiter? Let us consider these worlds in themselves. For the more one understands what Mars, Venus, and Jupiter represent, the more deliberate this trajectory begins to appear. Mars is the planet that nearly succeeded. 4 billion years ago, Mars harbored liquid water on its surface. Rivers carved valleys, and lakes filled craters. A denser atmosphere maintained surface temperatures conducive to chemical reactions, perhaps even the genesis of life. However, Mars is relatively small. Its core cooled, its magnetic field dissipated. Consequently, without this protective shield, the solar wind gradually stripped away its atmosphere, molecule by molecule, over hundreds of millions of years. Today, Mars is cold, arid, and its atmosphere is tenuous. The atmospheric pressure at its surface is less than 1% of Earth's, yet this thin atmosphere is composed of 95% carbon dioxide. And beneath the surface, dust lie ice deposits, subsurface water, remnants of ancient chemistry, the echoes of habitability. As 3 Atlas passes Mars at 0.19 astronomical units, it is encountering a world that tells a story of decline. Not a sudden catastrophe, but a gradual erosion, a process of extinction that spans eons. Throughout this period, spacecraft continue their observations from orbit. The Mars Reconnaissance Orbiter, with its high-resolution cameras, MAVEN, studying atmospheric escape, ExoMars, sniffing for methane, the Perseverance rover, drilling into rocks that may contain biosignatures. Mars is the most extensively studied planetary body after Earth. It is replete with sensors, and 3 Atlas will pass directly through this observation network. Venus is the world that deviated too far. It is remarkably similar to Earth in size and mass, having formed in the same region of the solar system. It likely began with comparable conditions, but something went awry. An uncontrolled greenhouse effect transformed Venus into a hellish environment. Surface temperatures hover around 470 degrees Celsius. The atmospheric pressure is 90 times that of Earth. Its clouds are composed of sulfuric acid. Carbon dioxide constitutes 96.5% of its atmosphere, making it the most CO2-rich environment in the inner solar system. Paradoxically, despite these extreme conditions, there is speculation about the possibility of life, not on the surface, but high within the clouds, where temperatures and pressures are more moderate. Microbes could potentially exist suspended in aerosols, deriving sustenance from sulfur compounds and carried by the winds. While this is a remote possibility, it is not entirely inconceivable. Venus also remains under constant observation. Japan's Akatsuki orbiter is meticulously charting Venus's atmosphere. NASA's Dainchi mission is poised to descend a probe through the cloud layers. The ESS Envision mission will employ radar to map the planet's surface. After decades of being largely overlooked, Venus is once again capturing the scientific world's attention. Amidst this renewed focus, the object known as 3I Atlas is traversing the cosmos, passing at a distance of 65 astronomical units from the Sun. Jupiter itself represents a realm of immense potential, though not Jupiter as a planetary body. It is merely a colossal sphere of hydrogen and helium, lacking a solid surface and subjected to unimaginable pressure. However, its moons, Europa, Ganymede, Callisto, and possibly Io, are worlds of profound interest. These are icy oceans, teeming with possibilities. Europa's surface is a complex tapestry of fissures and elevated ridges, suggesting the presence of a subsurface ocean warmed by tidal forces exerted by Jupiter's gravitational pull. Ganymede boasts its own intrinsic magnetic field and may harbor multiple strata of both ocean and ice. Callisto, while ancient and heavily bombarded, might conceal liquid water deep within its interior. These Jovian moons stand as prime candidates for harboring life beyond our own planet. This is not to suggest surface life, but rather life thriving in darkness, within the oceans, subsisting on chemical energy derived from hydrothermal vents. Furthermore, Jupiter's magnetosphere is the most extensive structure within our solar system, extending millions of kilometers into space as a vast bubble of charged particles and magnetic fields. Any celestial body traversing this region is subjected to its unique environment, characterized by intense radiation and electromagnetic interactions. If one were seeking to study a magnetosphere, Jupiter's would undoubtedly be the prime destination. On the 16th day of March, in the year 2026, 3I Atlas is scheduled to pass Jupiter at a distance of 0.35 astronomical units. The Juno spacecraft is already in orbit around the planet, diligently investigating its internal structure and magnetic field. The JUICE mission is en route, specifically engineered to scrutinize the icy moons. Europa Clipper is also expected to arrive shortly, dedicated to the study of Europa. The Jupiter system is on the cusp of becoming the most intensely explored region in the solar system, second only to Earth. 3I Atlas will glide through this dynamic environment just as all these new instruments become operational. 3 distinct worlds representing 3 distinct developmental stages. Mars, a seemingly defunct planet. Venus, a world that appears to have failed in its evolutionary trajectory. Jupiter, a system harboring worlds that may still harbor life. This presents a logical progression, a chronological sequence, an evolutionary narrative of planetary environments. Such a sequence is invaluable for comprehending how habitability arises, persists, or ultimately perishes. Were an advanced civilization to undertake a comprehensive survey of planetary systems, where would it direct its probes? It would target worlds that serve as critical data points, representing key stages. The objective would be to sample extreme conditions, desiccated atmospheres, dense atmospheres, and icy subsurface oceans. Such a survey would aim to measure the behavior of carbon dioxide across diverse environments and observe the interactions of magnetospheres with various planetary bodies. The ultimate goal would be to understand the full spectrum of possible outcomes. And critically, it would likely bypass Earth, the obvious choice, because Earth is already thoroughly known. Earth is the noisy world, the one actively broadcasting radio signals and launching spacecraft. Earth is the outlier, the place where life proliferated uncontrollably and a technological civilization emerged. It is possible that Earth was meticulously measured long ago, perhaps its data is already archived. The necessity for another close examination might be deemed redundant. Alternatively, Earth might be deliberately avoided for a different reason. It is conceivable that whoever initiated this survey, assuming such an entity exists, wishes to remain undetected. A close approach to Earth would invariably trigger every telescope, every radar installation, and every deep space tracking station in our possession, inevitably leading to significant global attention and potential responses. However, a passage by Mars, Venus, and Jupiter offers a far more discreet approach, a quiet corridor through which an object can conduct its operations without attracting undue notice. The statistical probability of this particular trajectory, calculated at less than 0.5%, remains a persistent point of contemplation. While coincidences do occur, This represents an exceptionally specific one, akin to threading three needles in succession, striking three targets that embody three distinct phases of planetary evolution, all while adhering to the orbital plane where our observational instruments are primarily focused. This could be a natural occurrence, or perhaps it is designed. Regardless, we are on the verge of gaining further insights because unlike Oumuamua, which we observed departing our solar system, 3I Atlas is presently within our reach. It is actively traversing these designated waypoints, and every telescope we can direct towards it is engaged in observation. However, a question that should truly occupy our minds is this. If this object is part of a larger pattern, if it is indeed conducting a survey, what will transpire once that survey is concluded? What happens when the data is gathered and transmitted? What occurs when the entity or entities responsible for these objects deem their information gathering complete? Will they return? Will they dispatch additional probes? Or will they simply update their records and depart, leaving us to ponder whether we were ever truly acknowledged? Part 5 delves into an emerging debate: natural comet versus engineered artifact. The scientific community is exercising extreme caution, recognizing that the instant one suggests an object might be artificial, a boundary is crossed. This shifts the discourse from mainstream astronomy to speculative conjecture, transforming a respectable researcher into an individual who is largely avoided at academic conferences. Consequently, the official, publicly stated consensus is unequivocal. 3I Atlas is classified as a comet. It is acknowledged as an unusual comet, but a comet nonetheless. The arguments supporting a natural origin are robust. The object exhibits a discernible coma, it is actively outgassing, and jets have been observed. Dust particles surround the nucleus, all of which are consistent with the sublimation of ice as the object approaches the sun, precisely the behavior expected of comets. The hyperbolic trajectory confirms its interstellar origin, but this does not inherently imply artificiality. Objects are routinely ejected from planetary systems due to gravitational interactions during planetary formation, sending countless bodies into the void. A fraction of these will invariably traverse into other star systems. The existence of interstellar comets has long been a theoretical certainty. Now we are beginning to detect them. The observed chemistry, while anomalous, is not outside the realm of possibility. As previously discussed, enrichment of carbon dioxide can occur through formation in frigid regions of a protoplanetary disk or via cosmic ray processing over billions of years. The estimated size, approximately a few kilometers in diameter, falls within the observed range of known comets. The rotational patterns, variations in brightness, and spectroscopic signatures can all be attributed to natural processes. Polarimetric studies, which measure how light scatters off the dust in the coma, reveal properties consistent with silicate grains and organic compounds, materials typically found in comets. There is no overt anomaly, no glaring inconsistency, no definitive proof of artificiality. Nevertheless, there are individuals who are posing critical questions, not fringe theorists or conspiracy enthusiasts, but serious researchers with impeccable credentials who are open to the hypothesis that we might be observing something more than a mere celestial rock. The trajectory remains the most compelling argument, that meticulously orchestrated passage through the planetary corridor, that precise inclination, that sequence of worlds representing stages of habitability. When the statistical probabilities are calculated, when the sheer unlikelihood of such a geometric alignment is considered, a sense of unease arises. 5% may not be zero, but it is sufficiently close to warrant deeper inquiry. Furthermore, the timing of the event is significant. 3. Atlas encounters these celestial bodies during a period when our observational capabilities are at their zenith. We possess more spacecraft in orbit around Mars than at any previous time. Missions to Venus are being intensified. The Jupiter system is poised to become the most extensively studied location in the solar system. If the objective were maximum observational coverage and data acquisition, timing a visit for precisely this juncture would be the optimal strategy. Is this mere coincidence? Probably, but it is a remarkably convenient one. Avi Loeb, the esteemed Harvard astronomer who garnered significant attention for his analysis of Oumuamua, has offered his perspective. He has advocated for rigorous scrutiny of interstellar objects for any indications of artificial origin. This is not based on a certainty that they are probes, but rather on the fact that the possibility, however remote, is not zero, and the implications, should it prove true, are immense. Even a 1% chance, he contends, warrants thorough investigation, data collection, and a proper process of elimination rather than outright dismissal. Other researchers, however, express reservations. They emphasize that the burden of proof is exceptionally high, asserting that extraordinary claims necessitate extraordinary evidence. Currently, the evidence suggesting 3I Atlas is anything other than a comet is, at best, circumstantial. Its trajectory is unusual, but not unprecedented. Its carbon dioxide chemistry is explainable. Its passage through the planetary corridor can be attributed to chance. The fundamental challenge lies in the fact that artificial and natural phenomena can exhibit remarkable similarities. If one were tasked with designing a probe intended to evade detection, mimicking the appearance of a comet would be a logical strategy. This would involve generating a coma, exhibiting outgassing, and closely matching expected chemical signatures. The most effective form of concealment is often to remain in plain sight. If this scenario is indeed unfolding, and this is a probe ingeniously disguised as a comet, then the only definitive means of confirmation would be to approach it closely. This would involve capturing high-resolution imagery, measuring accelerations that cannot be attributed to outgassing alone, and detecting some signal, structure, or behavior that transcends natural processes. However, we are not currently undertaking such measures. Launching a dedicated mission requires substantial funding, which in turn necessitates a scientific consensus. Achieving consensus hinges on the availability of concrete evidence, and thus we find ourselves back at the starting point. Consequently, the debate continues, unfolding within academic journals, at conferences, and in hushed conversations among researchers who are hesitant to voice their private thoughts publicly due to the profound implications involved. If 3I Atlas is a natural phenomenon, it represents an invaluable sample of another star system's chemistry, a crucial data point in our broader understanding of planetary formation across the galaxy. However, if it is artificial, then everything changes. The implications of an artificial origin are truly staggering. It would signify that we are not alone in the universe, that other entities exist, capable of interstellar travel, engaged in surveys, and cataloging other worlds. It would suggest that the galaxy might be populated by automated systems, quietly gathering data and transmitting it to unknown destinations. It would mean that we have been observed, measured, and classified. And if classified, what category would we fall into? Inhabited, technological, a threat, a resource, or simply another entry in a vast database, our entire existence reduced to a mere footnote? The hypothesis of a natural origin offers a sense of comfort, preserving the notion of a random universe and maintaining our perceived uniqueness, or at least our freedom from overt surveillance. However, the artificial hypothesis, despite its perceived improbability, compels us to confront possibilities for which we may not yet be prepared. It forces us to question whether the perceived silence of the galaxy is genuine silence, or whether we have simply been looking for the wrong kind of communication. Perhaps the message is not a radio signal or a laser beacon, but rather an object traversing space, navigating planetary systems, collecting data, and continuing its journey. A silent messenger, a reconnaissance probe, a surveyor, and perhaps we are only now beginning to recognize it for what it truly is. Part 6 explores the hypothesis of the instrument hitchhiker, where we, with our own instruments, are inadvertently observing it. Consider this thought experiment. If you wish to study a star system without revealing your presence, how would you proceed? You would avoid conspicuous spacecraft and refrain from broadcasting your arrival. Subtlety would be paramount, utilizing the system's existing infrastructure against itself. In our case, this infrastructure is remarkably extensive. We possess observational capabilities across the solar system. Orbiting Mars, the Mars Reconnaissance Orbiter and MAVEN XORs are continuously observing and recording. Venus is monitored by Akatsuki, with additional missions planned. Jupiter is under observation by Juno, with JUICE and Europa Clipper soon to join. On Earth, we have ground-based telescopes, space-based observatories, radar arrays, and deep space tracking networks. We have effectively constructed a surveillance system for our own solar system, dedicated to monitoring asteroids, studying planets, and tracking space weather. 3I Atlas is currently navigating directly through the heart of this observational network. The instrument hitchhiker hypothesis posits that the object is not attempting to evade detection, but is actively seeking it, positioning itself precisely where our instruments will inevitably observe, study, and analyze it. Every time we direct a telescope towards 3I Atlas, every time we capture a spectrum or an image, we are not merely observing the object. We are, in essence, revealing ourselves. Reflect on our actions. We are meticulously measuring its composition, tracking its trajectory, analyzing its structure, publishing our findings, and disseminating data. All of this information is being transmitted from observatories, relayed via satellites, and distributed across the Internet. If the object possesses any capacity for reception, it is actively learning about us while we believe we are learning about it. This concept is not as far-fetched as it may initially seem. We are aware that objects can carry instruments. Indeed, we have dispatched numerous such probes ourselves, including Voyager, Pioneer, and New Horizons. These are human-made spacecraft equipped with sensors, transmitters, and power sources designed for observation and data transmission. An advanced civilization could undoubtedly replicate this feat, but with far greater sophistication, creating smaller, more discrete probes concealed within natural-appearing bodies. The carbon dioxide coma could serve as an effective visual screen. When an object outgasses, it generates a cloud of dust and gas that obscures the nucleus, rendering fine details and surface features impossible to discern through the haze. Any structure or payload hidden within would be effectively masked. The greater the activity of the coma, the more effective the concealment. There is another relevant aspect to consider. The object is traversing regions where we have active spacecraft. Upon its approach to Mars, our Mars orbiters will be observing. As it nears Jupiter, Juno and the forthcoming missions will have opportunities for observation. However, these spacecraft are primarily designed for planetary study, not for intercepting interstellar visitors. Their instruments are pointed towards Mars or Jupiter, not at transient objects. While retargeting them is feasible, it presents significant logistical challenges requiring planning, fuel, and official approval. By the time approval is granted, the object may have already moved on. Consequently, the hitchhiker benefits from a free pass. It moves through our instrumented zones, is observed by ground-based telescopes which are more easily redirected, and all the while our most advanced spacecraft remain focused on their designated primary missions. This strategy is both efficient and elegant, exploiting an unforeseen vulnerability in our observational capabilities. However, a more profound question arises. If the object is intentionally designed to be observed, for what purpose? What is the objective of revealing oneself, even partially? One plausible explanation is a form of announcement, a subtle declaration. We are present, we are observing, and we wish for you to be aware of our existence. This is not conveyed through overt displays, but rather through objects precisely navigating your system, exhibiting distinctive chemistry, and following trajectories that provoke contemplation. Another possibility is a form of testing, a method of gauging our response. How swiftly do we detect their presence? How thoroughly do we analyze their characteristics? What instruments do we employ? How do we communicate our findings? All of this provides valuable insights into our technological sophistication, our coordination capabilities, and our priorities. Alternatively, the reason might be far simpler. Perhaps the object needs to transit these regions for other undisclosed purposes, such as resource acquisition, measurements, or trajectory adjustments, and being observed is merely an incidental consequence. This latter possibility might be the most disconcerting, the notion that our efforts to study this object are merely background noise to its actual mission. The instrument hitchhiker hypothesis also raises questions regarding reciprocity. If the object is observing us while we observe it, what is it learning? What data is it accumulating? And where is that data being transmitted? We lack this knowledge, and we likely cannot acquire it without getting significantly closer, utilizing instruments capable of detecting phenomena beyond typical cometary behavior. This presents a paradoxical situation. If the object is engineered to appear natural, our existing models for comets will align with our observations. We will perceive what we anticipate, and any anomalies will be rationalized away. The hitchhiker will then proceed undetected, having successfully completed its intended mission. This will persist unless we intensify our scrutiny, pose more insightful questions, and remain open to the possibility that not every object resembling a comet is, in fact, a comet. The object's passage through the Martian corridor is already in progress. The date of October 3, 2025 has either passed or is imminent, depending on when this information is accessed. Did any unusual events occur? Did the Mars orbiters detect anything anomalous? Did the object deviate from its course? Did it deploy any subordinate elements? We are observing, data is being collected, and somewhere individuals are analyzing that data, searching for the anomaly, the distinctive signature, the element that does not conform. Because if the instrument hitchhiker hypothesis holds true, then the evidence is present. We simply need to be willing to perceive it. Part 7 introduces the concept of the CO2 grazer, a resource harvester. Let us extend this line of inquiry further. What if the object's purpose extends beyond mere observation? What if it is actively acquiring resources? The persistent presence of elevated carbon dioxide levels remains a significant factor. An 8-to-1 ratio of carbon dioxide to water is not merely unusual, it is a pronounced indicator. When considering the object's trajectory, specifically its planned encounters with Mars and Venus, the two most carbon dioxide-rich environments in the inner solar system, it prompts speculation about whether this chemistry is coincidental or functional. Mars possesses a thin atmosphere, but it is composed of 95% carbon dioxide, exerting a pressure of approximately 6 millibars, roughly 6% of Earth's atmospheric pressure, with the entirety being carbon dioxide. Venus presents the opposite extreme, with an atmosphere comprising 96.5% carbon dioxide, but at a staggering pressure equivalent to 90 Earth atmospheres. This represents an immense reservoir of carbon dioxide. Venus's atmosphere contains significantly more carbon dioxide than any other body in the inner solar system, by orders of magnitude. And here we have 3I Atlas, enriched with carbon dioxide, passing sequentially by both of these worlds. The resource harvester hypothesis proposes that the object might be actively collecting carbon dioxide from these atmospheres. This may not be solely for propulsion, although that is a potential application. It could serve other purposes, such as chemical processing, energy storage, or as a feedstock for materials. Carbon dioxide, while a simple molecule, is remarkably versatile if one possesses the knowledge to utilize it. It can be dissociated into carbon and oxygen, combined with hydrogen to produce methane, employed as a working fluid, or compressed and liquefied for storage. An advanced probe designed for extended missions might require periodic replenishment of resources, not in the sense of rocket fuel, but in the replenishment of essential consumables. If the probe utilizes a chemical processing system, requires raw materials for repairs or self-replication, or stores energy in chemical bonds, then carbon dioxide would be an invaluable resource, making targeted approaches to CO2-rich worlds a logical strategy. The close approach to Mars, at 0.19 astronomical units, places the object well outside the planet's atmosphere. While direct atmospheric skimming is not feasible from such a distance, it allows for detailed measurements, mapping of atmospheric distribution, and identification of plumes or seasonal variations. Furthermore, if the object possesses any form of extended reach or a collection system that extends beyond its nucleus, it could potentially sample the outer fringes of the Martian exosphere. Venus presents a more compelling scenario. At 65 astronomical units, approximately 97 million kilometers, the object remains distant from Venus itself. However, Venus possesses a vast atmosphere that extends far into space. Its exosphere, the outermost layer from which atmospheric particles escape into space, reaches tens of thousands of kilometers above the surface. Continuous atmospheric stripping occurs due to interactions with the solar wind. Evidence of oxygen ions streaming behind Venus, shaped by solar radiation, has been observed. If the objective were to sample Venus's atmosphere without descending into its crushing depths, it would be accomplished from a distance by capturing escaping particles and measuring the outflow, and perhaps, just perhaps, by collecting some of it for its own use. This hypothesis necessitates that the object possesses capabilities extending beyond simple ice sublimation, implying active systems, collection mechanisms, and storage capacity. However, if one is already operating under the assumption that the object might be artificial, then these capabilities are not beyond reasonable conjecture. We have successfully designed spacecraft equipped with sample collection systems and missions dedicated to capturing particles for return to Earth. An advanced civilization could achieve similar feats, but without the requirement of a return journey, processing samples in situ, extracting necessary components, and discarding the remainder. The scientific counterargument to this hypothesis is straightforward. Comets sublimate. They do not harvest resources. The carbon dioxide detected in the object's coma originates from its nucleus, composed of ice that has remained frozen for billions of years. This substance is being released as the celestial body warms while nearing the sun, a completely natural and anticipated phenomenon, thus negating the need for invoking any collection mechanisms. However, the challenge lies in our inability to differentiate between these processes from afar. If the object is both sublimating its internal ice and simultaneously accumulating carbon dioxide from its planetary surroundings, our instruments would likely not distinguish between these two activities. We would observe a carbon dioxide coma and measure an outgassing rate, subsequently calculating the object's mass loss, all of which would align with existing comet models. The sole method to ascertain the truth would be to identify anomalies, deviations in its trajectory that cannot be attributed solely to outgassing, or asymmetric jets pointing in illogical directions. We might also observe fluctuations in its composition as it passes by different worlds, or, tellingly, an increase in its mass rather than a decrease. Currently, we are not detecting any of these phenomena with the required precision. Nevertheless, should the resource harvester hypothesis hold true, the object's behavior around Venus could provide crucial insights, as Venus represents an exceptionally rich source of carbon dioxide, possessing quantities thousands of times greater than Mars. Any deceleration, course alteration, or sudden surge or drop in its activity not correlated with solar radiation would be a significant indicator. This scenario carries broader implications. If interstellar probes require refueling or resource acquisition from the systems they visit, they would logically target worlds abundant in specific resources like carbon dioxide, water, or methane, and follow trajectories that maximize access. From our external viewpoint, such paths would appear deliberate and purposeful, suggesting design. This brings us back to the statistical improbability of its trajectory, a less than 0.5% chance. If its path is optimized for resource acquisition, it is not random. Such optimization mathematically translates to improbability. It is crucial to emphasize that this remains speculative. There is no definitive proof of harvesting, no observed mass increase, and no trajectory anomalies that necessitate extraordinary explanations. Thus far, the object has behaved like a comet. However, our observational campaign is still in its nascent stages. The encounter with Venus is yet to occur as of late October of the year 2025, and Jupiter remains months away. Data collection is ongoing. If the object is indeed harvesting resources, it is doing so with remarkable subtlety, precisely as one would anticipate for a mission designed to evade detection, taking just enough, maneuvering minimally, and keeping any detectable anomalies within the margin of measurement error. It operates at the very edge of detectability. This is a fundamental characteristic of advanced technology. It need not be overt or self-advertising. The most sophisticated technology is often the most unobtrusive, appearing entirely natural and seamlessly integrated. If civilizations are dispatching probes across the galaxy to survey planetary systems, they have had billions of years to perfect such camouflage. Therefore, we continue to observe, measure, and await anomalies, contemplating whether the carbon dioxide emanating from 3I Atlas is merely frozen chemistry from another star system, or if some of it originated from our own worlds, from the atmospheres we are only beginning to comprehend. Regardless of its origin, the object is acquiring something from this encounter: information, if nothing else, and perhaps that is all it requires. This leads us to Part 8, the planetary defense reconnaissance thread. There exists an alternative, more strategic and concerning perspective. What if the object's purpose is not sampling or harvesting, but rather assessing our capabilities? Planetary defense is a relatively new discipline. It is only within the past few decades that humanity has begun to seriously consider the threat posed by asteroid impacts. We have established surveillance systems like Atlas and Pan-STARRS, catalogued near-Earth objects, and even conducted tests, such as kinetic impactors, where spacecraft have been intentionally crashed into asteroids to determine the feasibility of altering their trajectories. The DART mission in 2022 definitively demonstrated our capacity to deflect an asteroid, thus confirming our existence of planetary defense capabilities, however rudimentary. Yet any capability inherently implies visibility. The development of a radar network for asteroid tracking simultaneously reveals the existence of such networks. Redirecting telescopes to monitor a new object showcases our responsiveness. Publishing analyses of trajectories and compositions demonstrates our scientific coordination. All of this constitutes valuable data. Should an advanced civilization wish to evaluate the defensive and technological prowess of a planetary system, dispatching an object through it and observing the ensuing reaction would be an effective method. This is the essence of the reconnaissance hypothesis. The object in this scenario serves as a probe, not for scientific investigation, but for intelligence gathering, military or, at the very least, strategic intelligence. It functions as a means to ascertain whether the system is passive or active, monitored or oblivious, unified or fragmented. Its carefully chosen trajectory through the planetary corridor places it precisely within the focus of our sensors. Every telescope that tracks it, every spacecraft that observes it, every published paper analyzing its characteristics contributes data points regarding our response time, instrument capabilities, inter-observatory coordination, and international cooperation, all of which are observable by any entity monitoring the situation. Let us analyze what the object has potentially learned thus far, assuming it is capable of learning. It was initially detected on the 1st of July, 2025, by the Atlas facility in Chile, not immediately upon entering the solar system, but weeks or months after crossing its outer boundaries. This provides information about our detection range. We can identify objects when they are relatively close, within a few astronomical units, but remain largely blind to the outer solar system, with the exception of the largest celestial bodies. Following its detection, the object was rapidly catalogued. Its orbital parameters were computed, predictions were formulated, and scientific papers were published, all within a matter of weeks. This indicates our capacity for swift analysis and characterization. However, it also highlights our reactive nature. We did not anticipate its arrival until it was already within our vicinity. Subsequently, observations were intensified. Ground-based telescopes worldwide commenced tracking its path, and space-based observatories, including the James Webb Space Telescope, were recalibrated for observation. Spectroscopic analysis began, measuring and openly sharing the object's composition, velocity, and trajectory. This demonstrates our data-sharing practices and collaborative approach, but also our lack of secrecy. Any entity with access to our communications would possess the same knowledge. The next phase involves the object's approach to Mars, Venus, and Jupiter, presenting opportunities for our spacecraft in those regions to conduct observations. However, redirecting a spacecraft is a complex undertaking requiring fuel, modifications to mission plans, and approvals from mission control, funding agencies, and international partners. This bureaucratic process is inherently slow, and by the time a decision is reached, the optimal observation window may have already closed. A reconnaissance probe would meticulously record these limitations, the sluggish institutional response, the divided lines of authority, and the inherent inflexibility of spacecraft designed for specific missions that struggle to adapt to new targets. These represent vulnerabilities and gaps in our observational coverage. Furthermore, there is the question of what remains unseen. The object's coma obscures its nucleus, preventing us from resolving surface features or detecting smaller structures. Any onboard instruments, antennas, sensors, or equipment beyond natural ice and rock are likely undetectable. Our highest resolution images depict a fuzzy sphere, yet even this provides crucial information to a reconnaissance probe. Our optical limitations. We possess the ability to detect and track, but lack the capacity for detailed observation of interstellar visitors at their immense distances. Finally, considering Earth itself, the object is actively avoiding a close approach to our planet, or at least not venturing particularly near. Earth, however, is an exceptionally noisy world, broadcasting radio signals, launching satellites, and illuminating the night side with its cities. Studying Earth from a distance would be entirely feasible without direct proximity. One could monitor the electromagnetic spectrum, observe artificial lights, and map infrastructure without ever entering its orbital space. By traversing past Mars, Venus, and Jupiter, the object is testing our response mechanisms without triggering our most heightened scrutiny. It remains just below the threshold of alarm, intriguing enough to warrant study, but not sufficiently threatening to necessitate a full-scale mobilization. This is a remarkably astute strategy, characteristic of a meticulously planned reconnaissance mission. The objective is to acquire data without eliciting a reaction that would, in turn, distort the data itself. This approach has historical precedent. During the Cold War, both the United States and the Soviet Union conducted reconnaissance flights along each other's borders, carefully avoiding airspace incursions, but remaining close enough to probe radar coverage, response times, and intercept capabilities. Observing an adversary's reaction to such probes yields significant intelligence regarding their capabilities, revealing vulnerabilities, measuring delays, and assessing coordination. If an entity is indeed surveying our solar system, it is employing a similar strategy, and we are inadvertently providing the necessary data, believing we are engaged in scientific inquiry, studying a comet. While this may be true, it is equally possible that we are simultaneously being studied in return. The object has exhibited peculiar jet activity. Images have captured a prominent jet, approximately 10,000 kilometers in length, directed towards the Sun. While this is a common characteristic of comets, as outgassing produces jets, these jets can also function as directional thrusters, imparting small amounts of momentum that can alter the object's trajectory. If the object is making minute course corrections to optimize its path, these adjustments might go unnoticed. The jets provide a plausible deniability for any observed maneuvers, allowing them to be attributed to natural outgassing. This presents the fundamental challenge of reconnaissance. When executed effectively, its presence remains entirely unknown. The probe appears natural, behaves naturally, and blends seamlessly into its environment. By the time it departs, it has gathered all necessary intelligence, leaving us none the wiser. So, what is our recourse? How can we defend against a potential threat that may already be present? The answer is sobering. We cannot, not yet. Defense requires a definitive understanding of the threat, and currently, we possess only suspicion and speculation, not certainty. Perhaps this uncertainty is precisely the objective. The reconnaissance might not be focused on assessing our weaponry or defensive systems, but rather on gauging our awareness. How long does it take for us to realize we are being observed? How long does it take to transition from classifying an object as an interesting comet to considering it a potential probe? How long before we initiate action? We remain in the interesting comet phase, implying that if this is indeed a reconnaissance mission, we are currently failing the test. Part 9 delves into the Trojan horse payload concealment angle. Imagine the design process for an interstellar probe intended to traverse star systems, collect data, and evade detection. The key is not invisibility, but rather the appearance of something familiar and natural. A comet serves as the perfect guise. Comets are ubiquitous celestial bodies composed of icy and rocky debris from planetary formation. Their tendency to outgaze when approaching a star creates a coma and tail that effectively obscure the nucleus. Their irregular shapes, variable brightness, and unpredictable behavior are well-established phenomena. Consequently, a comet is the ultimate camouflage for a probe. The coma, in this context, acts as a smokescreen, concealing whatever might be housed within the comet itself. The Trojan horse hypothesis posits that 3I Atlas might be concealing something, not necessarily a large, obvious spacecraft, but rather a payload. This payload could comprise small sensors, microprobes, transponders, or equipment designed for deployment at specific waypoints, with the coma providing the necessary cover. The mechanism would work as follows. The nucleus, estimated to be several kilometers in diameter based on brightness assessments, possesses substantial volume. While the majority of this volume consists of typical cometary material, ice, rock, and dust, it could also harbor something else, a payload hibernating and awaiting activation. As the object approaches the sun, it warms, causing the ice to sublimate and the coma to form. At predetermined points along its trajectory, at specific distances from designated planets, the payload would activate. Tiny probes, perhaps the size of a basketball or smaller, would be released. Coated in dust and resembling mere debris, they would drift away from the nucleus, carried by the outflowing gas, and becoming indistinguishable within the coma. Once liberated, these probes would employ small, efficient, and quiet thrusters, such as ion drives, to alter their course. They would then proceed towards their targets, Mars, Venus, or the moons of Jupiter, entering orbits, impacting surfaces, or positioning themselves in gravitationally stable regions where they could conduct observations for years, decades, or even centuries, all without our detection. This is because our focus would remain on the nucleus, tracking the primary body, while small objects within the coma would be mistaken for natural dust and debris. Our current resolution and tracking capabilities are insufficient for differentiation. Even with enhanced capabilities, identifying such artificial payloads would require a specific intent, as we are not currently programmed to search for them. The evidence supporting this hypothesis is largely circumstantial. The jets observed are a potential clue. The large jet directed sunward, noted by multiple telescopes, while characteristic of comets, could also serve as cover for directional thrust. A release of gas and dust, a plume of activity, could mask the deployment of a small probe, allowing it to discreetly separate. Polarimetry, the study of how light scatters off the coma, offers another intriguing piece of evidence. The observed scattering properties suggest the presence of dust grains that are more complex than simple silicates, potentially including organic compounds or even structured particles. While this is not conclusive proof of artificial origin, as comets can exhibit complex chemistry, it is a noteworthy observation. Additionally, the object's rotation pattern is relevant. Comets typically tumble or rotate as they traverse space, and these rotational patterns produce measurable variations in brightness. 3. Atlas has shown some variability, but its precise rotation pattern has not yet been fully characterized. If the object is deploying payloads and ejecting mass asymmetrically, this would inevitably affect its rotation, potentially leading to anomalies in its light curve, periods where brightness changes deviate from expected patterns. However, the inherent challenge lies in the fact that all these potential signatures, jets, polarimetry, and even rotation anomalies, can be explained through natural processes. Comets are inherently complex and chaotic entities, often defying simple models. Therefore, any deviation from predicted behavior can readily be dismissed as natural variability. Unless one is specifically looking for artificial payloads and analyzing the data with that hypothesis in mind, their presence would likely remain undetected. This is the ingenious aspect of the Trojan horse approach. It exploits our inherent assumptions. We assume comets are natural phenomena, that the coma is merely sublimating ice, and that jets are simply outgassing. This assumption prevents us from investigating further. Considering the potential functions of these hypothetical payloads, Mars represents the initial waypoint. A deployed payload could enter orbit or descend to the surface. Mars possesses a thin atmosphere which, with the aid of a heat shield, could facilitate atmospheric capture. Once on the surface or in orbit, a small probe could commence observations, monitoring rovers, tracking atmospheric changes, measuring the magnetic field, and transmitting data either to the parent object or directly into space. Venus presents a more formidable challenge due to its harsh atmospheric conditions. However, the upper atmosphere, at an altitude of 50 to 60 kilometers, offers a relatively benign environment with temperatures ranging from 0 to 50 degrees Celsius and Earth-like pressures. A small probe equipped with a balloon or airship could maintain indefinite buoyancy, sampling the clouds, observing the surface with radar, and functioning from a unique vantage point within Venus's environment where technology can endure. The moons of Jupiter represent the ultimate prize. Europa, Ganymede, and Callisto are celestial bodies believed to harbor subsurface oceans. A small probe landing on Europa could penetrate the ice crust or at least sample the surface material for biosignatures. Alternatively, it could establish an orbital position, measuring the induced magnetic field, mapping the ice shell, and awaiting a plume eruption to sample the ocean directly. All these scenarios are technically feasible with our current understanding of technology. Small probes, miniaturized instruments, solar panels or radioisotope power sources, and communication systems are all within our technological grasp. We have already developed devices like CubeSats and micro-rovers. An advanced civilization could undoubtedly achieve even greater levels of miniaturization, efficiency, and autonomy. Once deployed and dispersed throughout the solar system, these payloads would be exceedingly difficult to locate. They would likely operate silently and passively, observing without transmitting, or transmitting in ways currently beyond our detection capabilities, such as narrow-beam lasers or quantum entanglement. The Trojan horse hypothesis is particularly unsettling because it suggests that the object's passage is merely the prelude to a more extensive mission. The payloads it disseminates continue its work after its departure, observing, waiting, transmitting data back to their deployers, storing information for future retrieval, or functioning as nodes within a vast network, a galactic web of sensors silently cataloging the worlds they are tasked to monitor, all without our knowledge. We would observe 3I Atlas exiting the solar system, accelerating back into interstellar space, and consider the story concluded. We would publish our findings, analyze the data, and move on to the next celestial object. Meanwhile, a small machine, somewhere on Mars, within Venus's clouds, or on Europa's icy surface, would power up, extend its sensors, and commence its silent operation. This perspective might be considered paranoid, but paranoia, in essence, is the application of pattern recognition to potential threats. The patterns observed in this case, the precise trajectory, the unique chemistry, the calculated path through the planetary corridor, are too significant to disregard. If one were to dispatch Trojan horses into other star systems, this would be the method employed: concealment in plain sight, utilizing natural processes as cover, and targeting the most significant celestial bodies. This implies that if this hypothesis is accurate, we are no longer alone. We have visitors, small, silent observers who are not departing. Part 10 shifts to broader cosmic implications. Let us zoom out, far out, to comprehend the larger context. If 3i Atlas is part of a more extensive operation, we must examine the overarching picture. The emerging scenario is unsettling in its implications. To date, 3 interstellar objects have been definitively identified: ʻOumuamua in 2017, Borisov in 2019, and Atlas in 2025. These represent 3 distinct data points, 3 unique chemistries, and 3 divergent trajectories. ʻOumuamua was characterized as dry, elongated, and possibly tumbling, with no detectable coma. Borisov presented as wet and icy, exhibiting comet-like outgassing and a conventional appearance. Atlas, conversely, is rich in carbon dioxide, follows a retrograde path, and navigates the planetary plane with remarkable precision. 3 objects, each with a distinct signature. If this intentionality is beginning to strike you, you are not alone. Diversity in nature arises from varied formation environments, distinct histories, and a multitude of random events. However, diversity in design is typically driven by purpose. Different types of probes are dispatched to execute different tasks. Customization and specialization are key. One probe might be designed for arid inner solar system bodies, another for icy outer solar system bodies, and yet another for carbon dioxide-rich atmospheres. The same tool is not deployed universally, as environments differ. If these 3 objects are indeed elements of a network, nodes within a larger scanning system, their divergences become logical. They are not performing identical functions. Rather, they are sampling different aspects of the solar system, encompassing varied chemistries, distinct regions, and diverse timescales. This leads to a truly cosmic contemplation. If we have detected 3 such objects in less than a decade, how many are there in total? How many have evaded our detection? How many traversed our solar system before we possessed the technological capability to observe them? How many are currently out in the distant reaches of our solar system, too dim and far away for our observational efforts? The mathematics involved are disquieting. The success of detection is contingent upon an object's dimensions, its luminosity, its path of travel, and the extent of our search grid. We managed to identify perhaps 1% of the entities that traverse this region, possibly even less. This implies that for every visitor from beyond our stellar neighborhood that we manage to detect, scores, if not hundreds, slip by unnoticed. Furthermore, if these unobserved entities are also interconnected, forming part of a larger system, and are similarly navigating through our solar system, gathering information, then our solar system is far from vacant. It is, in fact, teeming with transient visitors. Now, let us broaden this perspective to encompass the entire galaxy. 200 billion stars, and countless planetary systems associated with them. If even a minuscule fraction of these are under observation, if merely 1% of star systems host automated probes passing through, then the galaxy is saturated with these mechanisms. A network of observation devices, a web of sensors, all traversing the cosmos, collecting data, and relaying it to some central point. This is the essence of the Census hypothesis. The concept that the galaxy is undergoing a systematic examination, not by piloted vessels or intrepid explorers, but by self-governing systems. Probes launched millennia or eons ago by civilizations that may no longer exist. These probes persist, adhering to their original programming, journeying from one system to another, meticulously documenting their findings. What exactly are they recording? Life? More likely, they are documenting habitability, the presence of biospheres, and indicators of technological advancement. Perhaps they are searching for something specific. Alternatively, they may simply be amassing data, engaging in a galactic-scale scientific endeavor spanning vast stretches of time. It's conceivable there's a central archive somewhere, a data repository spanning light years, where all this information is stored. Or it might be that each probe retains its own data, transmitting it to the next one it encounters, forming a cascade of information flowing through the galaxy, akin to neural impulses within an immense consciousness. The implications for SETI, the search for extraterrestrial intelligence, are profound. For decades, we have been actively listening for radio transmissions. Our assumption has been that if alien intelligences wish to communicate, they will broadcast. They will dispatch messages. They will make their presence unmistakable. But what if the primary objective is not communication? What if these probes are not here to engage in dialogue? What if their sole purpose is observation? In such a scenario, SETI's efforts have been misdirected. We have been straining to hear the heavens when our attention should have been focused on the objects passing through our own solar system. We have been seeking signals when the very object itself constitutes the signal. Its path is the message. Its elemental composition is the signature. Its transit is the proclamation. And if this is the case, then we have already experienced contact on multiple occasions. We simply failed to recognize it. We catalogued these objects. We subjected them to scientific study. We published our findings. Yet we neglected to pose the fundamental question: what is their purpose here? The Fermi paradox raises the question: if the galaxy is replete with intelligent life, where is everyone? Why have we not encountered them? Why does the universe appear silent? Perhaps the universe is not silent. Perhaps it is conveying subtle hints. Perhaps the messages are tangible rather than electromagnetic. Objects traversing space, passing through planetary systems, carrying information within their trajectories and constituent materials. And it is only now that we are beginning to decipher this language. This reframes our entire understanding. It suggests that the galaxy might be alive with intelligence, but not in the manner we have previously envisioned. Not through starships, nor colossal megastructures, nor radio beacons, but solely through probes, quiet, patient, navigating the darkness. Each one a single point in an image so vast that we cannot yet perceive it. Yet the image exists. The galaxy is being meticulously mapped, catalogued, and understood. And Earth itself is merely one data point, one frame within a narrative that has been unfolding for billions of years. We believe ourselves to be the protagonists. We perceive this as our story. However, we might merely be part of the background. We could be mere scenery. The narrative may not revolve around us at all. This realization is both humbling and terrifying, for it implies that we are not central. We are not unique. We are not the focus of cosmic attention. We are simply another planet within another system, quietly being observed by an entity we do not comprehend. However, here lies the intriguing aspect. If we are being catalogued, then we are an integral part of the data set. We are present in the records. Somewhere within a colossal archive, there exists an entry pertaining to Earth. A planet described as inhabited, technological, the third planet orbiting a yellow dwarf star. Possessing an atmosphere composed of oxygen and nitrogen, oceans of water, and life based on carbon. And perhaps there is an appended note: status active. Last update, October 2025. Next survey, pending. And if this is indeed the case, then someone, or something, is aware of our existence. They have measured us. They have classified us. The pertinent question then shifts from whether we are alone to what will transpire next. Will they return? Will they dispatch additional probes? Will they observe our evolutionary progression, waiting to ascertain if we successfully navigate our technological adolescence? Or will they simply update our file and proceed as if we were never even noticed? The answer remains unknown. However, these objects continue to arrive, and with each transit, with each detection of another interstellar visitor, the pattern becomes increasingly discernible. The underlying geometry grows sharper, and the possibility that we are part of something far grander, something ancient, patient, and immeasurably vast, becomes increasingly difficult to disregard. The galaxy is communicating. We are only just beginning to discern its language, and what it has to say may very well alter everything. Part 11. Breakthrough. Latest advancements in exoplanet biosignatures. While our focus has been on the objects traversing our solar system, a remarkable development has been unfolding beyond our celestial neighborhood. We are discovering life, or at the very least, the telltale signs that life leaves in its wake. In the year 2025, researchers announced the detection of a potential biosignature on an exoplanet orbiting a star approximately 40 light-years distant. This planet, a temperate world marginally larger than Earth, exhibited atmospheric indicators consistent with the presence of oxygen, ozone, and methane. These gases, in combination, present a compelling case for biological activity, making non-biological explanations exceedingly difficult. The detection was made possible by the James Webb Space Telescope, the same instrument that has been analyzing exoplanets using transit spectroscopy, a method that examines starlight as it filters through a planet's atmosphere. This finding is immensely significant. While not definitive proof of life, nor a direct observation, it represents a crucial signature, a chemical fingerprint. It is the kind of atmospheric composition that, on Earth, is exclusively produced by living organisms: oxygen generated through photosynthesis, methane from microbial activity, and ozone formed by the interaction of oxygen with ultraviolet radiation. Together, these gases create a chemical imbalance, a disequilibrium that would not naturally persist unless actively sustained by biological processes. And this is not an isolated occurrence. Over the past few years, the James Webb Space Telescope has been systematically surveying dozens of exoplanets in pursuit of these signatures. Several promising candidates have emerged, worlds with intriguing atmospheres and combinations of gases that could indicate the presence of life. While not yet conclusive evidence, these findings are sufficient to spark considerable speculation. Now, let us connect this to the narrative of Three-Eye Atlas. We find ourselves at a historical juncture where two distinct phenomena are converging. Firstly, we are unearthing evidence suggesting that life may be a common occurrence throughout the galaxy. Secondly, we are observing objects originating from other star systems as they pass through our own. When considered in tandem, these two facts paint a compelling picture. If life is indeed prevalent, if biospheres exist on planets orbiting other stars, then their detection becomes immensely valuable, not merely in a scientific context, but also from a strategic perspective. For any advanced civilization, understanding the distribution of life would be a paramount objective. They would seek to catalog it, map its presence, and comprehend its prevalence. The question then arises, how would they achieve this? Traveling from star to star themselves would be an inefficient and costly endeavor. Instead, they would deploy probes, automated systems, distributing them across the galaxy to undertake the observational work. Each probe would visit a star system, collect measurements, and then move on. Over millions of years, this would facilitate the compilation of an extensive database, a census of life across the cosmos. The detection of biosignatures indicates that life is, in fact, detectable. With the appropriate instrumentation, coupled with spectroscopic analysis and sustained observation, it is possible to identify a living world from vast interstellar distances. However, remote detection possesses inherent limitations. It does not allow for the detailed examination of specific characteristics. It does not permit close-up study of chemical processes. It cannot definitively ascertain whether the life detected is microbial or complex, unicellular or technologically advanced. For such granular understanding, direct visitation is required. The deployment of a probe is essential. And if 3i Atlas is indeed part of such a system, navigating through our solar system, measuring carbon dioxide levels, mapping magnetospheres, and sampling icy moons, then it is performing in situ observations that complement our remote sensing efforts. It is taking the subsequent crucial step, gathering ground truth data. This is why the object's trajectory is so significant. This is why its path through the Mars, Venus, and Jupiter corridor holds such profound meaning. These three celestial bodies represent distinct outcomes in terms of habitability. Mars, once possessing the potential for life, has since lost it. Venus, also a candidate for harboring life, experienced a runaway greenhouse effect, rendering it inhospitable. Jupiter's moons, on the other hand, possess the potential for life and may still harbor it. If the objective is to catalog biospheres, then these are precisely the data points one would need to collect. The aim is not only to identify where life currently exists, but also where it nearly arose, where it failed, and where it might still be concealed. Earth is the most obvious subject, easily identifiable. Earth's biosignatures, such as oxygen, methane, and the spectral signature of vegetation known as the red edge, are readily detectable from light years away. Earth announces its presence. However, the other worlds, those on the fringes of habitability, the marginal cases, necessitate closer scrutiny. And this is precisely what 3i Atlas is undertaking, assuming it is performing more than simply acting as a comet. The broader implication is that we are entering an era where the detection of life is becoming increasingly routine. The James Webb Space Telescope represents only the initial phase. Future telescopes will possess enhanced sensitivity, and observational surveys will become more comprehensive. Within decades, it is plausible that we will possess a catalog of hundreds of potentially habitable worlds, each with detailed atmospheric data, each representing a candidate for harboring life. And if we are diligently constructing such a catalog, why would an entity, particularly an older civilization with millions or billions of years of development, not have already accomplished this? Why would they not have probes distributed across the galaxy, systematically visiting star systems, gathering measurements, and filling in the crucial details that remote observation is incapable of providing? The exoplanet biosignature detections do not constitute definitive proof of the sensor hypothesis, but they provide invaluable context. They demonstrate the feasibility of life detection. They suggest that the galaxy may be teeming with biospheres awaiting discovery. And they illustrate that if the intention were to map these biospheres, the necessary technology already exists. We are achieving this with telescopes. They, perhaps, are achieving it with probes. The simultaneous detection of biosignatures in distant worlds and interstellar objects within our own solar system may not be mere coincidence. It could signify the moment when humanity finally comprehends that the galaxy is far more expansive, vibrant, and interconnected than we had ever imagined. And if this is indeed the case, then 3i Atlas is not merely an object. It is a harbinger, an announcement, a signal that we are not alone in our quest to find life. Someone else is searching too, and they have been doing so for a considerably longer period than we have. Part 12. Breakthrough. Advances in magnetosphere and planetary environment studies. While our attention has been captivated by 3i Atlas as it navigates the inner solar system, another significant development has been occurring in the vicinity of Jupiter. The data emerging from missions such as Juno has fundamentally transformed our understanding of the Jovian system. This impact extends beyond Jupiter itself to its moons, Europa, Ganymede, and Callisto. These celestial bodies are no longer merely icy spheres. They are worlds possessing oceans, complex environments, and the potential to harbor life. Europa has been the primary focus. NASA's Juno spacecraft, which has been in orbit around Jupiter since 2016, has conducted close flybys of Europa in recent years. The data gathered has revealed that Europa's subsurface ocean is likely global, extending tens of kilometers in depth and containing more liquid water than all of Earth's oceans combined. Crucially, this ocean is in direct contact with a rocky seafloor, implying the presence of active geological and chemical processes, including the dissolution of minerals and the potential for hydrothermal vents, environments strikingly similar to those where life may have originated on Earth. However, a new and compelling discovery has emerged. In 2025, researchers analyzing Juno's magnetometer data detected variations in Europa's induced magnetic field. These fluctuations suggest that the ocean is not static, it is actively circulating. The presence of currents, possibly convection cells, and temperature gradients indicates a dynamic ocean, implying a continuous flow of energy. And where there is energy, there exists the potential for life. Ganymede presents an even more complex scenario. It possesses its own intrinsic magnetic field, a unique characteristic among the solar system's moons. This field interacts with Jupiter's immense magnetosphere, creating a miniature magnetosphere surrounding Ganymede itself. Beneath this magnetic shield lies an ocean, or perhaps multiple stratified oceans separated by ice shells of varying phases. The sheer complexity of this system is staggering. Callisto, the outermost of Jupiter's large moons, appears less active and more quiescent. Yet even Callisto may harbor a subsurface ocean concealed deep beneath its ancient, heavily cratered surface. If Callisto, the least promising candidate, possesses liquid water, then the habitability of the Jovian system is even more extensive than previously believed. All of these findings hold significant relevance for 3i Atlas, given its trajectory towards this region. On March 16, 2026, the object is projected to be at a distance of 0.35 astronomical units from Jupiter. This proximity places it closer to Jupiter than many of its moons. It will traverse Jupiter's magnetosphere, experiencing intense radiation and being exposed to charged particles and electromagnetic fields. If the object's purpose is to measure magnetospheres and sample planetary environments, then Jupiter represents the ultimate prize. Jupiter's magnetosphere is the largest structure in the solar system, excluding the Sun itself, extending millions of kilometers. It traps charged particles originating from the solar wind and from the volcanic plumes erupting from Io. It interacts with the moons, inducing currents within their subsurface oceans. An object passing through this region could meticulously measure all these aspects: field strength, particle density, plasma composition, and the intricate interactions between the magnetosphere and the moons. If the goal were to understand how magnetospheres shield or expose subsurface oceans, or to determine if electromagnetic interactions could facilitate life-supporting chemistry, then Jupiter would be the optimal location for such investigations. Furthermore, the timing is remarkably opportune. By March 2026, the European Space Agency's JUICE mission is scheduled to arrive at Jupiter, and NASA's Europa Clipper will either be en route or already in position. Juno will still be operational. Consequently, the Jovian system will be the most instrumented and extensively observed location in the solar system, outside of Earth itself. Multiple spacecraft equipped with magnetometers, spectrometers, cameras, and radar will be actively collecting data. And through this formidable array of sensors, 3i Atlas will pass. This scenario lends significant weight to the instrumented hitchhiker hypothesis. If the object is designed to be observed, if it is deliberately positioning itself within the reach of our instruments, then the Jupiter encounter emerges as the central event of its mission. All preceding observations of Mars and Venus would constitute mere preliminary stages. Jupiter is where the data collection becomes exceptionally rich, where our observational capabilities align perfectly with the object's trajectory. However, there is an alternative perspective. The ongoing studies of planetary magnetospheres reveal that these environments are far from simple. They are not merely empty expanses surrounding planets. They are dynamic, active zones teeming with particles, fields, and complex interactions that we are only beginning to comprehend. If the objective were to conceal something, or to deploy payloads or conduct measurements discreetly, the magnetosphere would serve as an ideal cover. The background noise is substantial, and the environment is inherently chaotic. Small anomalies would easily be lost within the natural fluctuations. A probe released into Jupiter's magnetosphere could drift for years, propelled by electromagnetic fields, observing the moons as it passed them. It could position itself near Europa, monitoring for plume activity and sampling particles should an eruption occur. It could orbit Ganymede, studying the interplay between the moon's magnetic field and Jupiter's. It could even settle into a stable Lagrange point and simply observe, remaining undetected by us. This is because Jupiter's environment is vast, and our instruments are predominantly focused on the moons themselves. We are examining Europa's surface, Ganymede's interior, and Callisto's craters. We are not actively scanning empty space for small, silent objects that reflect minimal light and emit no discernible signals. The advancements in magnetosphere science also underscore the critical role these environments play in habitability. Europa's ocean is kept in a liquid state primarily by tidal heating. However, the magnetosphere contributes significantly. Charged particles bombard the surface, breaking down water ice and generating oxygen. Some of this oxygen may eventually make its way into the ocean, providing a potential energy source for life, an electron donor, a crucial component of biochemistry. If an entity were conducting a survey of habitable environments, it would be imperative to measure these interactions. Remote sensing alone cannot provide data on magnetosphere interactions. Direct presence within the environment is required, with instruments measuring field strength, particle flux, and radiation dosage. And if 3i Atlas is equipped with such instruments, or if it is capable of deploying smaller probes that carry them, then the Jupiter encounter represents the pivotal moment of its mission, determining its success or failure. There is also the question of what the object itself will experience. Traversing Jupiter's magnetosphere at a distance of 0.35 astronomical units signifies exposure to exceptionally intense radiation. Jupiter's radiation belts are notoriously severe, capable of damaging electronic components and even organic molecules. If 3i Atlas is a natural comet, this radiation will interact with its surface, processing the ice and inducing chemical changes. If it is an artificial construct, the radiation poses a significant challenge, necessitating robust shielding, hardening, and redundancy in its design. The object's behavior during and after its passage through Jupiter's magnetosphere could provide invaluable insights. Will it maintain its projected trajectory? Will it exhibit signs of damage? Will its outgassing patterns undergo alterations? Any anomaly, Any deviation from its predicted behavior will be highly significant. This is because natural objects respond to radiation in predictable ways. Artificial objects, if expertly designed, would exhibit a different response. They would compensate, adapt, and survive. We will not have definitive answers for some time. The Jupiter encounter is still some months away, but the necessary infrastructure is rapidly being put into place. Juno is prepared. JUICE is en route. Europa Clipper is also on its way. The instruments are being calibrated, and observation plans are being meticulously formulated. And when 3i Atlas arrives, we will possess an unparalleled vantage point for observing an interstellar visitor interacting with a planetary environment, the likes of which we have never had before. If there is a hidden secret to be revealed, if there is a definitive signature that proves this object is more than a mere comet, then Jupiter is where we are most likely to find it. This is because Jupiter does not conceal, it amplifies. Its magnetosphere acts as a magnifying glass, a natural laboratory where any anomaly is rendered conspicuous, and 3i Atlas is heading directly into its heart. The magnetosphere studies conducted in 2025 have illuminated the active, complex, and potentially habitable nature of these environments. They have demonstrated the crucial role of electromagnetic interactions in supporting life. They have revealed that the Jovian system is not merely of interest, it is of paramount importance. It represents a nexus, a hub, a region where multiple potentially habitable environments converge around a single colossal planet. If one were designing an optimal survey route, if one were planning a trajectory for maximum data acquisition, Jupiter would undoubtedly be included, not simply to pass by, but to traverse the magnetosphere, to sample the environment, and to meticulously measure the intricate interactions. And this is precisely what 3i Atlas is undertaking. Is this merely a coincidence? Perhaps, but the coincidences are accumulating at an unprecedented rate. The trajectory, the chemical composition, the timing of arrival, the available instrumentation, each of these factors, considered individually, is explainable. However, when viewed collectively, they form a distinct pattern, and patterns, by their very nature, convey meaning. Part 13, Breakthrough: Artificial Intelligence in Spacecraft Autonomy and Deep Space Monitoring. Another significant development in 2025, worthy of considerable discussion, is the substantial advancement in our ability to construct autonomous spacecraft. This progress is particularly relevant when contemplating the possibility of interstellar probes, objects designed to traverse between stars and conduct extensive surveys. Autonomy, in this context, represents the pivotal technological enabler. It is simply not feasible to have human operators involved when the nearest star system is light years away. The requirement is for systems capable of independent decision-making and operation. Both NASA and the International Space Agency, ISA, successfully demonstrated highly advanced AI-driven spacecraft systems this year. These included small probes equipped with onboard decision-making capabilities, coordinated swarms of CubeSats operating without ground control interventions, and sophisticated deep learning algorithms empowered to identify targets, formulate trajectories, and execute complex maneuvers without requiring direct commands from Earth. This is not imaginative storytelling. It's active technological deployment undergoing evaluation right now. Consider the Autonomous Cosmic Body Surveillance Network as one illustration. This is a collection of miniature spacecraft powered by artificial intelligence, capable of identifying, tracking, and classifying celestial objects in Earth's vicinity. These satellites independently determine their observation targets, calibrate their instruments, assign priority to specific objects, and share gathered information amongst themselves. Crucially, they accomplish all these tasks at speeds unattainable by human-controlled systems. Another pertinent illustration is the realm of deep space exploration. Contemporary Mars rovers and orbital probes are equipped with autonomous navigation. They can circumvent obstacles, plot optimal paths, and collect specimens based on scientific directives, all without the impediment of signal latency. Mars is several minutes away by light speed. Transmissions can take between 10 and 20 minutes to reach the planet's surface. Effective immediate reaction necessitates self-governing capability. Now, envision this principle extended significantly. Not light minutes, but light years. An exploratory vessel venturing beyond our solar system cannot request guidance from home. The time required for a signal to travel to its destination and return is measured in years, decades, or even centuries. Consequently, such a probe must possess intrinsic intelligence. It needs to make autonomous judgments, identify objectives, adjust its course, deploy its equipment, gather data, store it, transmit it when feasible, recover from malfunctions, and adapt to its surroundings. The critical realization here is this: if we are currently constructing systems of this magnitude with our present technological capacity, then an advanced civilization possessing millions or billions of years of further development could undoubtedly create something vastly more sophisticated. Imagine a system that not only executes pre-programmed instructions, but actively learns. A system capable of improvisation, able to arrive in a new star system, evaluate the environment, and decide on its course of action without any external direction. This is precisely the operational requirement for an interstellar probe. It must be more than a passive instrument or a rigidly sequenced automaton. It must be an intelligent entity, an explorer, an independent agent. If 3i Atlas embodies such a system, if it represents something beyond a mere cometary body, then all our observations begin to coalesce into a coherent picture. Its trajectory, meticulously threading the planetary passage, its autonomous navigation, selecting an optimal route, its chemical composition, harmonizing with the target environments, its adaptive concealment or deliberate structural makeup, its timing coinciding perfectly with our observational windows, its apparent awareness of our technological infrastructure. An AI-driven probe would not require substantial size. It would be free from the necessity of immense propulsion systems or colossal instrumentation. Instead, it would be efficient, compact, and self-sufficient. It would leverage local resources, extracting materials from asteroids or planetary atmospheres. It would enter a dormant state during protracted interstellar journeys, conserving energy. Upon detecting a star system, it would awaken, assess the situation, and act accordingly. Our capacity to detect anomalies is also progressively improving. Machine learning algorithms are now employed to scrutinize astronomical data, identifying patterns that might elude human observation, such as unusual light fluctuations or unexpected spectral signatures and trajectory deviations. These algorithms have successfully identified exoplanets, confirmed supernovae, and detected gravitational waves, and their proficiency continues to grow annually. Should an entity aim to conceal an artificial construct amongst natural phenomena, it would need to account for these detection advancements. Their efforts would require a subtlety sufficient to bypass machine learning analysis, implying either flawless camouflage or deliberate yet natural-appearing prominence. The strategy would involve either merging so seamlessly with the natural background that no algorithm can discern its artificiality, or exhibiting characteristics that appear natural enough to be dismissed as such. 3i Atlas might be navigating this delicate balance, exhibiting enough peculiarity to warrant attention, yet maintaining sufficient normalcy to be plausibly explained, existing precisely on the threshold of detectability. Furthermore, the concept of interconnected networks is highly relevant. Our artificial intelligence systems are increasingly evolving towards distributed intelligence, functioning as swarms, collectives, and integrated systems where multiple small units collaborate, sharing data and coordinating actions. No single unit holds ultimate authority. The overarching intelligence emerges from their collective interactions. If interstellar probes operate on a similar principle, then 3I Atlas is not an isolated entity, but part of a larger network. ʻOumuamua was part of this network. Boris was part of this network. Each one acting as an independent agent, yet all interconnected in some fashion, exchanging information and coordinating efforts to construct a collective understanding of the galaxy. We are currently incapable of detecting such coordination. The communication methods employed may be beyond our current monitoring capabilities, perhaps utilizing frequencies or channels we haven't yet conceived of, such as quantum entanglement, gravitational waves, neutrinos, or some other exotic phenomenon. Alternatively, this communication might unfold gradually over years or decades, characterized by patience and method, as time holds little urgency for an immortal machine. The advancements in spacecraft autonomy observed in the year 2025 demonstrate the feasibility of such capabilities. We are currently implementing these principles on a smaller scale, developing systems that can think, explore, and adapt. If we can achieve this with mere decades of computer science progress, it follows that others elsewhere could perfect such systems. This understanding is crucial because it fundamentally alters our approach to detection. Historically, we have searched for overt indicators, broadcast signals, constructed megastructures, or anomalous accelerations. However, an AI-driven probe would deliberately avoid conspicuous signs, operating with careful methodology. It would observe without intervention, blending seamlessly with its surroundings. The sole avenue for detecting such a system lies in identifying subtle anomalies, statistical improbabilities, trajectories exhibiting excessive precision, chemical compositions appearing remarkably opportune, or timings that are impeccably perfect. These are precisely the characteristics we are observing with 3I Atlas. While not definitive proof, these observations are certainly suggestive. In the absence of concrete evidence, suggestive data is all we possess. The AI breakthroughs of 2025 also illuminate another potential scenario. What if these probes are not merely collecting data, but actively learning? What if each interaction with a planetary system refines their models, enhances their strategies, and deepens their comprehension? An AI that has been operational for millennia, visiting countless star systems, would possess extraordinary sophistication. It would understand how to approach a system without triggering alarm, know precisely what to measure and where to focus its instruments, and be capable of interpreting signs of life, technology, and habitability. It would function as an expert surveyor. If 3I Atlas fits this description, then we are being examined by an entity that comprehends its mission entirely, an entity that has undertaken such tasks numerous times previously. Whatever conclusions it draws about us, whatever data it compiles, will be integrated into a repository spanning the entire galaxy. This realization is both humbling and somewhat unsettling, as it implies we are not merely being observed, but are being understood by something utterly beyond our comprehension. Part 14, Pioneering Solar System Interceptor Missions and Swift Responses to Small Celestial Bodies. Here lies a significant challenge. We are now adept at detecting interstellar objects. We have established observational surveys and developed algorithms to monitor for unusual trajectories. However, mere detection is insufficient. We must be able to intercept these objects, to approach them closely, conduct measurements, and potentially obtain material samples. Our current capabilities in this regard are inadequate. In the year 2025, both NASA and the European Space Agency, ESA, released proposals for rapid response interceptor missions. The underlying concept is straightforward. Upon the detection of an interstellar object, a compact high-speed spacecraft would be launched to overtake it. This would not necessitate a large-scale mission or years of meticulous planning. Instead, it requires a spacecraft maintained in a state of readiness, a launch vehicle prepared for immediate deployment, and a trajectory calculation that can be performed swiftly. ESA's Comet Interceptor mission serves as the prototype. It is designed to launch and then await deployment at a Lagrange point, a stable gravitational position, until a suitable target is identified. Once a target is confirmed, the spacecraft would depart its holding orbit to achieve interception. It would not need to rendezvous or enter orbit. It would simply perform a high-speed flyby, collecting data during the brief encounter. NASA is pursuing analogous concepts, focusing on small spacecraft equipped with ion drives capable of sustained acceleration over several months or years, thereby accumulating sufficient velocity to intercept an interstellar visitor even after its outward trajectory has been identified. The requisite technology is available. The primary obstacle is preparedness. And here lies the source of frustration. We missed ʻOumuamua. By the time we recognized its unique nature, it had already departed our solar system. We managed to acquire a limited number of measurements, but none were detailed. There were no close-up images or in-situ analyses. It is now beyond the reach of any mission we could realistically launch. We achieved a better outcome with Boris, benefiting from a longer observation window and collecting more data, yet we still did not manage an interception. We observed it from a considerable distance. Now, with 3i Atlas, we are observing in real time. We know its location and its projected path, yet we are not dispatching any craft to meet it, at least not yet. The reason is that interceptor missions demand considerable time for planning, funding, construction, and launch. By the time we are prepared, the object will have moved beyond our reach. This constitutes the critical gap, the inherent vulnerability. We can observe these objects, but we cannot interact with them physically. And if they harbor secrets, if they are more than they appear, we will never ascertain this by merely observing from Earth. The significant advancement is that we are finally treating this matter with the seriousness it deserves. Rapid response programs are receiving funding, and the necessary technology is under development. By the time the next interstellar object arrives, we may well be prepared. We might have a spacecraft on standby, capable of launching within weeks rather than years. However, this raises a pertinent question. If we are preparing to intercept future visitors, are they aware of this? If 3i Atlas is part of a surveillance network, does it possess knowledge of our developing interceptor capabilities? Does it regard this as significant? Perhaps this is an integral part of their assessment. Perhaps the survey is not solely gauging our present technological capacity, but also our developmental trajectory. How rapidly we progress, the duration it takes us to transition from detection to interception, and whether our approach is reactive or proactive. If this is the case, then our response to these objects is itself data, and whoever dispatched them is observing our reactions. There is another perspective to consider. Interception capability also signifies defensive capability. A spacecraft equipped to intercept a comet could equally intercept a missile. A network capable of tracking small celestial bodies can also track military assets. The technology possesses dual-use applications, and if we are developing it, we are sending a clear signal. We are conveying, "We are aware of you. We possess the means to reach you. We are not a passive entity." This could fundamentally alter the strategic calculus. If these probes are assessing threat levels, if they are evaluating whether a technological civilization poses a danger or is benign, then our capacity for interception becomes critically important. This represents a transition point, moving from observation to action, from a passive stance to an active one. And perhaps this is when circumstances will shift, when the next phase will commence. Because if we can intercept, if we can physically interact with these objects, then we can determine their true nature. We can resolve the fundamental question: are they natural or artificial, random occurrences or deliberate creations, coincidences or intended actions? The interceptor missions planned for 2025 and 2026 represent humanity's initial serious endeavor to bridge this gap, to transition from mere observation to physical engagement. And when that moment arrives, when we finally capture one of these visitors and retrieve data uncorrupted by the vast distances of space, we will possess definitive knowledge. We will ascertain whether the galaxy is devoid of life or teeming with it. We will determine if we are alone or under observation. We will discover if these objects are messengers, scouts, or something else entirely beyond our current conceptualization. Until then, we will continue to watch, to wait, and to construct our interceptors, for the next visitor is on its way, and this time we intend to be ready. Part 15. Concluding Synthesis and Future Outlook. What is the overarching significance of all this for us? Let us consolidate our findings. Let us consider what all of this signifies, not merely for scientific inquiry or astronomical pursuits, but for humanity itself, for our perception of our place within the cosmos. 3I Atlas entered our solar system on the first day of July, 2025. It is navigating a precisely defined path through the planetary corridor, passing Mars, approaching Venus, and heading towards Jupiter. Its trajectory is characterized by remarkable accuracy. Its chemical makeup exhibits unusual properties. Its arrival timing is remarkably convenient. When considered collectively, these facts coalesce to form a narrative that is increasingly difficult to disregard. The prevailing scientific consensus is clear. This is a comet, an interstellar comet possessing characteristics that are unusual but explainable. Its hyperbolic orbit suggests an origin from another star system. Its CO2-rich composition could be attributed to its formation environment or cosmic ray processing. Its retrograde trajectory, which happens to be nearly coplanar with the planetary orbits, is presented as a statistical coincidence, a manifestation of natural variability. This is the conservative interpretation, the one that avoids extraordinary assertions. After all, extraordinary claims necessitate extraordinary evidence. Presently, the evidence is circumstantial and suggestive, though not conclusive. It is intriguing, but not definitive. Yet, there is always a caveat. The trajectory intersects the paths of 3 celestial bodies, each representing a distinct stage of potential habitability. The chemical composition aligns with the conditions found on those worlds. The timing coincides with periods of maximal observational coverage. The statistical probability is low, but not zero. And with each new piece of data, each subsequent measurement, another layer appears to be added to the discernible pattern. If this were the sole interstellar object encountered, it might be dismissed. However, it is not. ʻOumuamua was distinct. Boris was distinct. And Atlas is distinct. 3 objects, each with unique chemical compositions and trajectories. And if one is actively seeking a pattern, the prevailing theme is diversity, purposeful diversity. The speculative hypotheses we have explored, such as an instrument hitchhiker, a resource harvester, a reconnaissance probe, or a Trojan horse payload, remain unproven. They are possibilities, intellectual exercises, avenues for posing what-if scenarios. But it is precisely through what-if that all discovery originates. What if the Earth orbits the Sun? What if microscopic organisms cause disease? What if the universe is expanding? What if we are not alone? And what if 3I Atlas is indeed more than just a comet? This question carries profound implications. If it is artificial, if it is part of a surveillance network, then the galaxy is being systematically observed, mapped, and catalogued by an entity that is ancient, patient, and operates on temporal scales we can barely comprehend. If this premise holds true, then Earth is already documented. We have been measured, our atmosphere analyzed, our biosphere catalogued, and our technological advancements noted. And whatever system is accumulating this data possesses a record pertaining to us. Homo sapiens, a technological species residing on the third planet, currently active. This understanding should fundamentally alter our self-perception. We are not isolated. We are not undiscovered. We are integrated into a broader context, a galactic ecosystem. And whether we find this realization agreeable or not, we have been acknowledged. However, there is a crucial distinction. Being noticed does not equate to direct communication. 3I Atlas is not decelerating. It is not broadcasting signals. It is not attempting to establish contact. It is merely passing through, gathering data, and continuing its journey. We represent merely one stop on an exceptionally long voyage. And perhaps this is the most unsettling aspect of all. Not that we are being observed, but that we are not particularly noteworthy. We are merely a data point, a sample, a single entry in a catalog that likely encompasses thousands or millions of other worlds. We are not unique. We are not central. We are simply another inhabited planet within a galaxy that may be replete with them. This represents the Copernican principle taken to its logical extreme. Earth is not the center. The Sun is not the center. Our galaxy is not the center. And perhaps our existence itself is not particularly remarkable. For centuries, we have progressively shifted our perceived position from the center of all things to the periphery, from the pinnacle of creation to a pale blue dot orbiting an average star in an average galaxy. And now it is conceivable that we are merely another entry in someone else's extensive database. However, an alternative interpretation exists. Perhaps we are being deliberately left uncontacted. Perhaps there is an established protocol, a governing principle. The directive might be, do not interfere with developing civilizations. Allow them to mature. Let them navigate their own evolutionary path. Observe from a distance, but refrain from direct engagement. Not yet. The deliberate threading of the planetary corridor, the avoidance of Earth, the subtle passage through instrumented zones, all of this could be indicative of careful non-interference. It could be a method of observation that avoids disruption, a means of data acquisition that does not alter the observed outcome. Scientists on Earth adhere to specific protocols when studying endangered species. They observe without intervention, collect measurements without modifying behavior, and document their findings without causing disruption. It is plausible that whoever dispatched these objects follows similar ethical guidelines. Perhaps there is a galactic code of conduct that dictates allowing civilizations to develop naturally, avoiding contamination of the experiment. If this is the case, then the crucial question becomes, when will this non-interference cease? When will we transition from being observed to being acknowledged? Is there a specific threshold, a technological milestone, or a behavioral indicator? And if we cross it, what will be the consequence? Perhaps the threshold is the advent of interstellar travel. Perhaps when we achieve the capability to reach other star systems ourselves, when we become active participants in the interstellar community rather than merely inhabitants of a single planet, that is when contact will occur. Perhaps they are awaiting our initiative to join them rather than coming to us. Alternatively, the threshold might be something entirely different. It could be related to how we treat each other, how we manage our planet, or whether we successfully navigate our technological adolescence. There is a concept in astrobiology known as the Great Filter. The premise is that somewhere between the emergence of single-celled life and the establishment of a galaxy-spanning civilization, there exists a formidable barrier. This barrier is something that most species fail to surmount. Potential candidates include climate collapse, nuclear warfare, the uncontrolled development of artificial intelligence, or engineered pandemics. It is conceivable that the ongoing survey is assessing which civilizations successfully overcome this filter and which ones do not. And if we are being catalogued, if our status is being regularly updated, then our future actions may directly influence the next update. Will we find solutions to climate change, or will we allow it to escalate uncontrollably? Will we wield our technology wisely, or will we engineer our own destruction? Will we unite as a species, or will we fragment into perpetual conflict? These are not merely abstract questions for us, they may represent critical data points for those who are observing us. We do not know. We cannot know, at least not without further data. And that data is forthcoming. The passage by Venus is imminent, or perhaps has recently occurred, depending on when you are receiving this information. The encounter with Jupiter is scheduled for months from now. Every available telescope is focused on this object. Every spacecraft within its projected trajectory is on alert. And perhaps this time we will discover the anomaly, the telltale signature, the irrefutable evidence that it is not merely a comet. Or perhaps we will not. It might pass through, behaving precisely as a natural celestial body would, leaving us to our speculations and persistent questions. Regardless of the outcome, the discourse has fundamentally shifted. We are no longer asking if interstellar objects exist. We know they do. We are now inquiring about their nature, their significance, and whether they are messengers, scouts, or something entirely beyond our current vocabulary. And this, in itself, represents progress. This is humanity engaging in its most fundamental characteristic, observing the universe and questioning its underlying reasons, identifying patterns and contemplating their meaning, and transforming raw data into narratives that may, just may, hold a kernel of truth. The scientific method mandates skepticism. It requires us to refrain from hasty conclusions, to meticulously gather evidence, to rigorously test hypotheses, and to maintain an openness to the possibility of being mistaken. This is a valuable principle, as it safeguards us from succumbing to superstition and pseudoscience. However, skepticism should not morph into outright denial or blindness. Exercising caution in drawing conclusions should not preclude us from recognizing discernible patterns. And the pattern we are observing here, whether natural or artificial in origin, is undeniably worthy of thorough examination. Because here is what we know with absolute certainty. Interstellar objects are a reality. They traverse our solar system, originating from distant star systems, places where different suns illuminate alien worlds and diverse planetary bodies orbit. Each one serves as a sample from another locale, a fragment of a different neighborhood delivered directly to our doorstep. And whether they are composed of natural cosmic debris or are meticulously engineered probes, they possess immense value. They offer us glimpses into the broader expanse of the galaxy. The truly unsettling revelation is not that Three-Eye Atlas is approaching us. It is that it does not need to. We have already been measured, catalogued, and classified. Earth is but one data point in an automated census of life that has been ongoing for a period far exceeding the existence of our species. Somewhere in the vast darkness, an ancient system is diligently updating its records, noting which worlds continue to sustain life and which have fallen silent. And we are now inscribed within that database. Our status reads, active, inhabited, technological. Status, ongoing. Consider this carefully. Status, ongoing, not complete, not finished, but ongoing. We are still in flux, still undergoing evolution, still developing. And whoever or whatever is maintaining these records possesses the patience to observe our ultimate outcome. Whether we will thrive or collapse, whether we will aspire to reach the stars or turn inward and fade into obscurity. This realization is simultaneously humbling and empowering. It serves as a lesson in humility, showing us we are not as central as we once believed. The cosmos does not orbit around our existence. We are not the principal focus. Yet this realization also bestows empowerment, affirming our capacity for action. Our narrative remains unwritten. The conclusion is not preordained. Our actions possess significance, even if that significance is merely a single data point among countless others. The unfolding events are within our purview. We have the option to disregard this, to dismiss the observed patterns as mere happenstance, and to revert to the comforting notion that we are solitary. This is the path of least resistance, the secure choice. It requires no alteration in our self-perception or our place within the vastness of space. Alternatively, we can embrace this with seriousness. We can engage in preparation. We can construct our interceptor craft. We can enhance our observational capabilities. We can formulate more incisive inquiries. We can conduct ourselves with the awareness that we may be under scrutiny, adjusting our behavior accordingly. This is not about succumbing to paranoia or fear, but rather about cultivating awareness, thoughtfulness, and intentionality in our actions and the messages we transmit. For if we are being observed, if these celestial bodies are part of an investigative process, then every facet of our existence is exposed. Our conflicts, our achievements, our stewardship of this planet, our endeavors to transcend its boundaries, all of it constitutes data. All of it is being meticulously recorded, and, perhaps, all of it is being assessed. This is not intended to instill dread, but rather to foster clarity. If we are constituents of something far grander, if our presence is being catalogued within a cosmic framework, then our obligations extend beyond our immediate selves. We are not merely custodians of Earth. We are its representatives, its envoys, irrespective of our prior intentions. And this fundamentally alters our perspective. It imbues our actions with universal importance, not due to any inherent uniqueness, but because we are under observation, because somewhere a consciousness or entity is meticulously documenting our deeds, noting our responses to the challenges we encounter. We are living in a period where this concept is transitioning from abstract speculation to tangible reality. When interstellar objects shift from theoretical possibilities to empirically observed phenomena, when the question of our solitude evolves from philosophical debate to empirical data analysis, when the galaxy ceases to be a remote concept and becomes an immediate, palpable presence. As these objects continue to arrive, each one presents an opportunity for discovery and learning, potentially confirming that the universe is indeed vaster, more enigmatic, and more alive than we had ever dared to imagine. The object designated as 3 Atlas will depart. It will accelerate back into the void of interstellar space, fading from our telescopic view until it is lost to us. Its coma will disperse. Its trajectory will carry it beyond our detection capabilities, rendering it a spectral presence, a mere echo in astronomical archives. However, this is not a conclusion, but rather a genesis. We now comprehend what to seek. We recognize the underlying pattern. We understand that interstellar visitors traverse our solar system along paths that, at times, suggest deliberate intent. We acknowledge their diversity in composition and behavior. We note their passages near worlds of potential astrobiological significance, and we observe their frequency, which implies they are not as uncommon as once believed. When the subsequent visitor appears, when another interstellar object navigates our system with improbable precision, we will be prepared. We will be vigilant. And perhaps this time we will approach closely enough to ascertain its true nature. Perhaps this time our interceptor craft will be deployed. Perhaps this time we will be able to directly sample its substance, capture high-resolution imagery, and detect any artificial elements, should they exist. Conversely, we may confirm its natural origin. We might discover that the universe is simply a realm of profound strangeness, governed by chance and an abundance of coincidences. And that revelation, too, would be significant. For either outcome, whether artificial or natural, imparts a profound understanding of the galactic environment we inhabit. Until that moment arrives, we wait. We gaze at the heavens, contemplating whether, in some distant expanse, something is observing us in return, quietly documenting, patiently recording, updating cosmic archives. And perhaps, just perhaps, pondering whether we will ever decipher this enigma. Wondering if we will discern the pattern. Wondering if we will grasp its meaning. Wondering if, when that understanding finally dawns, we will be equipped to comprehend its ramifications. The universe is communicating. It has been doing so all along, through transient nocturnal visitors, through inexplicable trajectories, through chemical signatures sufficiently anomalous to provoke contemplation. And now, at last, we are beginning to heed its message. What we discern may instigate transformative change or prove inconsequential. In either case, we are attending, and this act of listening in itself represents progress. It signifies humanity's reach beyond its immediate confines, its pursuit of vital inquiries, its search for answers in the sole location they can be found, the distant darkness from which these visitors originate. The narrative of 3 Atlas has not concluded, it has merely commenced, and we are now intrinsically a part of it, whether we acknowledge it or not. Every individual who gazes upon the night sky, every scientist who meticulously analyzes data, every person who contemplates its implications, we are all witnesses to an event that could be the most pivotal discovery in human history, or it could simply be a comet. Regardless, it warrants our full attention, for the universe seldom grants us opportunities to glimpse beyond our immediate cosmic vicinity. And when it does, when it dispatches visitors from distant star systems, we owe it to ourselves to observe with discernment, to reflect with depth, and to question with sincerity. This is what 3 Atlas has bestowed upon us, not definitive answers, but rather questions. More refined questions, deeper inquiries, questions that may ultimately illuminate our position within a universe far more intricate and interconnected than we ever conceived. And this is a realization worth celebrating. It is a pursuit worth undertaking. It is a reason to remain awake and attentive.